What if everything you thought you knew about the beginning of the universe was just the tip of the iceberg? Picture this, a single moment, an explosion of energy so immense that it set the stage for everything we see, feel, and know. But what if that moment, the Big Bang, wasn't what we've always believed it to be? What if it was something stranger, something more mysterious, something that defies our very understanding of reality? Tonight, we're diving into the cosmos to explore some of the most mind-bending theories about the Big Bang, ideas that challenge everything we think we know about the universe's origins. From black holes birthing new realities to universes colliding in higher dimensions, these theories will take you on a journey that stretches the limits of imagination. So, get comfortable, close your eyes, and let's drift into the stars as we uncover the strange and fascinating possibilities of how it all began. And as we begin this cosmic adventure, I'd love to know, where are you joining us from, and what time is it there? Let's connect across the universe as we explore its greatest mysteries together. Now, let's venture into a theory that turns the very idea of the Big Bang on its head. Imagine this. What if the Big Bang wasn't the beginning of everything, but rather the aftermath of something even more extraordinary? Some scientists propose that the Big Bang could have been the result of a black hole explosion in another universe. Yes, you heard that right. A black hole explosion. Black holes are often thought of as cosmic vacuum cleaners, sucking in everything around them, including light. But what if they are more than just destructive forces? What if they're gateways to other dimensions, or even other universes? This theory suggests that when a black hole collapses or explodes in one universe, it could create a new universe in another dimension. Think of it like a cosmic ripple effect. One universe's end could be another's beginning. This idea ties into the concept of the multiverse, where countless universes exist alongside our own, each with its own set of physical laws and realities. If the Big Bang was indeed the result of a black hole explosion in another universe, it would mean our universe is just one link in an infinite chain of cosmic events. It's a mind-bending thought, isn't it? But how does this theory hold up? While it's still largely speculative, some scientists point to the behavior of black holes and the mysterious nature of singularities, points of infinite density, as potential clues. If a black hole singularity could somehow punch through into another dimension, it might explain how our universe came to be. This theory not only challenges our understanding of the Big Bang, but also opens up a whole new realm of possibilities about the nature of existence itself. Could our universe be just one of many, born from the remnants of another? As we ponder this, let's keep our minds open to the infinite mysteries that the cosmos holds. And with that, we're ready to explore the evidence and implications of this fascinating idea. Now, as we delve deeper into this intriguing theory, let's examine the evidence that could either support or challenge the idea that the Big Bang was the result of a black hole explosion in another universe. One of the key pieces of evidence scientists look to is gravitational waves. These ripples in space-time, first detected in 2015, are often created by massive cosmic events like black hole collisions. If the Big Bang was indeed triggered by a black hole explosion, it's possible that traces of gravitational waves from that event could still linger in the fabric of our universe. While we haven't yet detected such waves directly linked to the Big Bang, their existence opens the door to the possibility that our universe's birth was part of a much larger cosmic chain reaction. Another critical piece of evidence comes from the cosmic microwave background radiation, often referred to as the afterglow of the Big Bang. This faint radiation fills the universe and provides a snapshot of the early cosmos. Some researchers suggest that subtle irregularities in this radiation could hint at the influence of a black hole explosion from a previous universe. These irregularities might carry clues about the conditions that existed before our universe began, offering a tantalizing glimpse into the multiverse theory. However, interpreting these patterns is no easy task, and scientists are still working to unravel their full meaning. The implications of this theory are profound. If the Big Bang was indeed the result of a black hole explosion in another universe, it would mean that our universe is not a standalone entity, but part of an infinite web of interconnected realities. This idea challenges the traditional view of the Big Bang as a singular, unique event, and instead paints a picture of a cyclical cosmos where universes are born, die, and give rise to new ones in an endless cycle. It also raises questions about the nature of time, space, and existence itself. Could the laws of physics vary from one universe to another? And if so, what does that mean for our understanding of reality? As we ponder these questions, it's important to remember that this theory, while fascinating, is still in its early stages. The evidence we have is indirect, and much of it remains open to interpretation. Yet, the very possibility that our universe could be part of a larger multiverse is a thrilling concept that pushes the boundaries of human knowledge. It invites us to think beyond the confines of our own reality and consider the infinite possibilities that lie beyond. With that in mind, let's continue our journey into the cosmos, where even more strange and wondrous theories await. Now, shifting our gaze to another fascinating theory, let's explore the idea that the Big Bang was not a singular explosion, but the result of a collision between two branes. In the realm of string theory, branes, short for membranes, are multidimensional objects that exist in higher dimensional space. Imagine these branes as vast, floating sheets, each representing a universe in its own right. According to this theory, our universe was born when two of these branes collided, releasing an immense amount of energy that sparked the Big Bang. This concept not only redefines our understanding of the universe's origins, but also introduces the possibility of a cyclical cosmos, where such collisions happen repeatedly, giving rise to new universes over and over again. The idea of a cyclical universe is both captivating and profound. If the Big Bang was indeed caused by a brane collision, it suggests that our universe is just one chapter in an endless cosmic story. Each collision could create a new universe, complete with its own laws of physics and unique properties. This theory aligns with the concept of the multiverse, where countless universes exist alongside ours, each born from similar cosmic events. It also raises intriguing questions about the nature of time and space. Could the collision of branes be a recurring event, happening at regular intervals across the vast expanse of higher dimensions? And if so, what does that mean for the future of our own universe? One of the most compelling aspects of this theory is how it ties into the broader framework of string theory. String theory proposes that the fundamental building blocks of the universe are not particles but tiny, vibrating strings. These strings exist in higher dimensions, and branes are the surfaces on which they can attach. When two branes collide, the energy released from their interaction could set off a Big Bang, creating a new universe. This idea not only provides a potential explanation for the Big Bang, but also offers a glimpse into the intricate dance of higher dimensional physics. It suggests that our universe is just one layer in a much larger, multidimensional reality. As we consider the implications of this theory, it's important to note that it remains speculative. While the mathematics of string theory and brane cosmology are elegant, they are also incredibly complex, and direct evidence for branes or higher dimensions has yet to be found. However, the very possibility that our universe could be the result of a brane collision opens up a world of new questions and avenues for exploration. It challenges us to think beyond the three dimensions we experience and imagine a cosmos filled with hidden layers and infinite possibilities. With this theory in mind, we're reminded once again of the boundless mysteries that the universe holds. The idea of a cyclical cosmos, born from the collision of branes, invites us to rethink our place in the grand tapestry of existence. As we continue our journey through these strange and wondrous theories, let's keep our minds open to the infinite possibilities that lie beyond the limits of our current understanding. Now, as we venture further into the realm of brane cosmology, let's explore the fascinating role of higher dimensions in shaping our universe. The idea that our reality extends beyond the familiar three dimensions of space and one of time is both mind-bending and essential to understanding how the Big Bang might have unfolded. In this framework, higher dimensions are not just abstract mathematical concepts. They are the very fabric that allows branes to exist and interact. These extra dimensions, often hidden from our perception, could hold the key to explaining some of the universe's most profound mysteries, such as its uniformity and the enigmatic force known as dark energy. Imagine the universe as a vast, multidimensional tapestry. While we experience only a small slice of this tapestry, our three-dimensional space, the higher dimensions are where the real action happens. According to brane cosmology, the collision of branes in these higher dimensions could have set off the Big Bang, creating the universe as we know it. But here's where it gets even more intriguing. The properties of these higher dimensions might explain why the universe appears so uniform on a large scale. When branes collide, the energy released could spread out evenly across the higher dimensional space, leading to the smooth distribution of matter and energy we observe in the cosmic microwave background radiation. This uniformity, often referred to as the cosmic horizon problem, is one of the great puzzles of cosmology, and higher dimensions offer a compelling solution. But the role of higher dimensions doesn't stop there. They could also shed light on the mysterious force driving the universe's accelerated expansion, dark energy. In brane cosmology, the energy trapped within the higher dimensions could manifest as dark energy in our observable universe. This energy, acting as a kind of cosmic pressure, might be pushing the universe apart at an ever-increasing rate. The idea that dark energy originates from higher dimensions is still speculative, but it provides a tantalizing connection between the unseen layers of reality and the forces shaping our cosmos. It challenges us to think beyond the limits of our perception and consider that the answers to some of the universe's biggest questions might lie in dimensions we cannot yet see. As we reflect on the implications of higher dimensions, it's worth noting how this theory bridges the gap between the very large and the very small. On one hand, it offers a cosmic scale explanation for the Big Bang and the universe's structure. On the other, it ties into the microscopic world of string theory, where the fundamental building blocks of reality are tiny, vibrating strings existing in these same higher dimensions. This duality between the vast and the minuscule highlights the elegance of brain cosmology and its potential to unify our understanding of the universe. With this deeper dive into higher dimensions, we're reminded once again of the boundless complexity and beauty of the cosmos. The idea that our universe is just one layer in a multidimensional reality invites us to rethink everything we thought we knew about space, time, and existence itself. As we continue to explore these strange and wondrous theories, let's keep our minds open to the infinite possibilities that lie beyond the limits of our current understanding. Now, shifting our gaze to the quantum realm, we encounter a theory that challenges our very understanding of existence itself. The idea that the Big Bang could have been a quantum fluctuation in a pre-existing void is as profound as it is perplexing. To grasp this concept, we must first venture into the strange and unpredictable world of quantum mechanics, where the rules of classical physics no longer apply. Here, particles pop in and out of existence, and the fabric of reality is governed by probabilities rather than certainties. It's a realm where the impossible becomes possible, and where the birth of the universe might find its origins. At the heart of this theory lies the concept of quantum fluctuations, tiny, random changes in energy that occur even in the emptiest regions of space. In the quantum world, a vacuum is never truly empty. Instead, it's a seething sea of potential, where pairs of particles and antiparticles spontaneously appear and vanish in an instant. These fleeting disturbances are a fundamental feature of quantum mechanics, and they suggest that something can indeed arise from nothing. But how does this relate to the Big Bang? Imagine a pre-existing void, a state of absolute nothingness, where quantum fluctuations could occasionally produce enough energy to trigger a massive event. In this scenario, the Big Bang wasn't the beginning of everything. It was the result of a quantum anomaly, a ripple in the void that set the stage for the universe we know today. The principles of quantum mechanics provide a framework for understanding how such an event could occur. One key idea is the uncertainty principle, which states that we can never precisely know both the position and momentum of a particle at the same time. This inherent uncertainty allows for spontaneous energy fluctuations, even in a vacuum, Another crucial concept is quantum tunneling, where particles can tunnel through barriers that would be insurmountable in classical physics. Together, these principles suggest that the universe could have emerged from a quantum fluctuation, tunneling into existence from a state of nothingness. It's a radical idea, but one that aligns with the unpredictable nature of the quantum world. What makes this theory particularly compelling is its ability to address the question of why there is something rather than nothing. If the universe began as a quantum fluctuation, it means that existence itself could be the result of a random, yet inevitable, event. This challenges our traditional notions of cause and effect, suggesting that the universe might not have needed a specific cause to come into being. Instead, it could have simply been a statistical inevitability, a product of the quantum laws that govern reality at its most fundamental level. As we ponder the implications of this theory, it's worth considering how it connects to other ideas about the universe's origins. For instance, the concept of a multiverse, where countless universes exist alongside our own, could arise naturally from quantum fluctuations. Each fluctuation could give birth to a new universe, each with its own unique properties and laws of physics. This idea not only expands our understanding of the Big Bang, but also opens the door to an infinite array of possibilities, where our universe is just one of many in a vast cosmic tapestry. The theory that the Big Bang was a quantum fluctuation invites us to rethink the very nature of existence. It suggests that the universe might not have a single, definitive beginning, but rather emerged from the chaotic, unpredictable realm of quantum mechanics. As we continue to explore this idea, we're reminded of the profound mysteries that still surround the origins of our cosmos. The quantum world, with its strange and counterintuitive rules, offers a glimpse into the forces that might have shaped the universe, and perhaps into the very fabric of reality itself. Now, as we delve deeper into the quantum realm, let's explore the fascinating role of virtual particles in the story of the Big Bang. These elusive entities, though fleeting, hold the key to understanding how something as vast as the universe could emerge from what we perceive as nothingness. Virtual particles are not like the particles we encounter in everyday life. They exist only for the briefest moments, popping into and out of existence in the quantum vacuum. This vacuum, far from being empty, is a dynamic and energetic space where the rules of quantum mechanics reign supreme. It's here, in this seemingly barren void, that the seeds of the universe may have been sown. The concept of virtual particles arises from the uncertainty principle, which allows for temporary violations of energy conservation. In the quantum vacuum, pairs of particles and antiparticles spontaneously form, borrowing energy from the vacuum itself before annihilating each other and returning the energy. These fleeting disturbances are not just theoretical. They have real, measurable effects, such as the Casimir effect, where two uncharged metal plates placed close together experience an attractive force due to the pressure of virtual particles between them. This phenomenon demonstrates that even in a vacuum, the quantum world is teeming with activity, and this activity could have played a crucial role in the birth of the universe. Imagine for a moment that one of these quantum fluctuations didn't immediately cancel itself out. Instead, it grew, fueled by the energy of the vacuum, until it triggered a massive expansion, a Big Bang. This idea suggests that the universe could have begun as a quantum anomaly, a rare but inevitable event in the chaotic dance of virtual particles. It's a radical departure from the traditional view of the Big Bang as a singular, explosive event, offering instead a picture of the universe emerging from the probabilistic nature of quantum mechanics. In this scenario, the universe isn't the result of a grand design or a specific cause. It's the product of the inherent unpredictability of the quantum world. The philosophical implications of this theory are profound. If the universe arose from a quantum fluctuation, it challenges our deepest assumptions about existence. Why is there something rather than nothing? This question, which has puzzled philosophers and scientists for centuries, finds a possible answer in the quantum vacuum. The universe, in this view, doesn't need a creator or a first cause. It could simply be the result of the natural laws that govern the quantum realm. This idea shifts the focus from seeking a definitive beginning to understanding the processes that make such beginnings possible. It suggests that existence itself might be an emergent property of the quantum vacuum, a consequence of the fundamental laws of physics. Moreover, this theory invites us to reconsider the nature of nothingness. In the quantum world, a vacuum is not empty. It's a seething, dynamic space filled with potential. What we perceive as nothing is, in fact, a rich and fertile ground from which something can arise. This redefinition of nothingness aligns with the idea that the universe could have emerged from a state that, to our classical understanding, appears to be void. It's a reminder that the quantum world operates on principles that often defy our intuition, offering a glimpse into the profound mysteries of existence. As we reflect on the role of virtual particles in the Big Bang, we're drawn into a deeper exploration of the universe's origins. This theory not only provides a scientific framework for understanding how the universe could have begun, but also challenges us to rethink our place in the cosmos. If the universe arose from a quantum fluctuation, it means that we are part of a reality that is both random and inevitable, shaped by the unpredictable yet lawful nature of the quantum world. It's a humbling and awe-inspiring perspective, one that invites us to continue exploring the mysteries of the cosmos with curiosity and wonder. With this in mind, let's turn our attention to another intriguing theory, one that suggests the Big Bang might have been a white hole event, the cosmic opposite of a black hole. This idea opens up new possibilities for understanding the universe's expansion and the flow of time, offering yet another layer to the enigmatic story of our origins. Now, shifting our gaze to a cosmic counterpart, let's explore the idea that the Big Bang might have been a white hole event. White holes are often described as the opposite of black holes. While black holes pull everything in, never letting anything escape, white holes are theorized to expel matter and energy outward, refusing to let anything enter. Imagine a cosmic fountain, endlessly spewing out material into the universe. This concept, though still speculative, offers a fascinating twist on the story of the Big Bang. If the Big Bang was a white hole explosion, it would mean that the universe began not with a collapse, but with an eruption. In this scenario, the white hole would have released all the energy and matter, that now forms the cosmos, creating the conditions for galaxies, stars, and planets to emerge. This theory aligns with the idea that the universe is expanding, as the white hole's outward force would naturally drive this growth. But unlike the traditional Big Bang model, which suggests a singular, explosive event, the white hole theory implies a more continuous process, with matter and energy being ejected over time. One of the most intriguing aspects of this theory is its connection to the concept of time. In the realm of general relativity, white holes are often considered to be black holes running backward in time. While a black hole represents a point of no return, where time seems to slow and stop at the event horizon, a white hole could represent a point of no entry, where time flows outward, pushing matter and energy into the universe. This reversal of time's direction offers a unique perspective on the Big Bang, suggesting that the universe's birth might be intimately tied to the nature of time itself. However, the white hole theory is not without its challenges. For one, white holes have never been observed, and their existence remains purely theoretical. Unlike black holes, which have been detected through their gravitational effects and the radiation they emit, white holes lack any direct evidence. Additionally, the laws of thermodynamics pose a significant hurdle. White holes would need to violate the second law of thermodynamics, which states that entropy, or disorder, always increases over time. For a white hole to expel matter and energy, it would have to decrease entropy, which contradicts our current understanding of physics. Despite these challenges, the white hole theory continues to captivate scientists and thinkers alike. It offers a fresh perspective on the universe's origins, challenging us to rethink the nature of time, space, and the fundamental laws of physics. If white holes do exist, they could provide a bridge between the quantum world and the cosmos, offering insights into how the universe began and how it might evolve in the future. This theory reminds us that the cosmos is full of mysteries waiting to be unraveled, and that even the most speculative ideas can lead to profound discoveries. As we ponder the possibility of a white hole Big Bang, we're reminded of the boundless creativity of the universe. Whether or not this theory holds true, it invites us to explore the edges of our understanding, to question the assumptions that shape our view of reality, and to embrace the wonder of the unknown. With this in mind, let's venture further into the cosmic tapestry, where even more enigmatic theories await. Now, as we delve deeper into the cosmic enigma, let's consider how white holes might intertwine with another fascinating concept: wormholes. Wormholes, often depicted in science fiction as shortcuts through space and time, are theoretical tunnels that could connect distant points in the universe, or even different universes altogether. If white holes and wormholes are connected, it could offer a groundbreaking explanation for the universe's expansion and the mysterious flow of time. Imagine a white hole as one end of a cosmic tunnel, spewing out matter and energy, while a wormhole serves as the bridge linking it to another region of space or time. In this scenario, the Big Bang could be seen as the moment when a white hole erupted, releasing the contents of the universe through a wormhole-like structure. This would not only explain the sudden appearance of matter and energy, but also provide a mechanism for the universe's rapid expansion. The wormhole could act as a conduit, channeling the universe's initial burst into the vast expanse we observe today. This connection between white holes and wormholes also sheds light on the nature of time. If a wormhole links 2 points in space-time, it could create a loop where time flows differently at each end. For instance, time might move forward in one region while reversing in another, offering a possible explanation for the arrow of time, the one-way direction in which time seems to flow. This idea aligns with the notion that white holes are black holes running backward in time, suggesting a cyclical relationship between these cosmic phenomena. However, the idea of white holes and wormholes being connected is not without its challenges. Wormholes, like white holes, remain purely theoretical, and their existence has yet to be proven. The immense gravitational forces required to stabilize a wormhole would demand exotic forms of matter with negative energy, which have never been observed. Additionally, the laws of physics, as we understand them today, struggle to accommodate such structures without leading to paradoxes or contradictions. Despite these hurdles, the potential connection between white holes and wormholes continues to inspire scientists and theorists. It offers a tantalizing glimpse into the possibility of a universe where space and time are far more interconnected than we ever imagined. If such a connection exists, it could revolutionize our understanding of the cosmos, revealing new pathways through space-time and offering insights into the origins and fate of the universe. As we explore this intricate web of cosmic possibilities, we're reminded that the universe is a place of endless wonder and mystery. The interplay between white holes and wormholes challenges us to think beyond the boundaries of conventional physics, inviting us to imagine a reality where the fabric of space-time is far more dynamic and interconnected than we ever dreamed. With this in mind, let's continue our journey through the cosmos, where each theory opens new doors to understanding the grand tapestry of existence. Now, shifting our gaze to a theory that bends the very fabric of reality, let's explore the idea that the Big Bang might not have been a physical event at all, but rather a holographic projection. This concept, known as the holographic principle, suggests that our three-dimensional universe could be a two-dimensional projection of information, much like a hologram. Imagine the cosmos as a vast cosmic screen, where every star, galaxy, and particle is encoded on a flat surface, and what we perceive as reality is simply a projection from that surface. The holographic principle stems from the study of black holes and the surprising discovery that the information about everything that falls into a black hole is somehow preserved on its surface or event horizon. This led scientists to propose that the universe itself might operate in a similar way, with all the information about its contents encoded on a boundary, and our experience of space and time being a kind of illusion. If this is true, the Big Bang could be seen as the moment when this two-dimensional information was projected into the three-dimensional universe we inhabit today. This theory challenges our traditional understanding of the Big Bang as a physical explosion of matter and energy. Instead, it suggests that the universe's birth was more like the activation of a cosmic projector, where the information stored on a two-dimensional surface was translated into the three-dimensional reality we observe. This idea not only redefines the nature of the Big Bang, but also raises profound questions about the nature of reality itself. Are we living in a universe that's fundamentally flat, with depth and dimension being mere illusions? Could the entire cosmos be a kind of hologram, with every event and object encoded on a distant, unseen surface? The implications of the holographic principle are staggering. If the universe is a projection, it could mean that space and time are not fundamental aspects of reality, but emergent properties arising from deeper, more abstract layers of information. This would fundamentally alter our understanding of physics, suggesting that the laws governing the universe might be more about information processing than physical interactions. It also opens the door to new ways of thinking about the origins of the universe, as the Big Bang could be reinterpreted as the moment when this information began to unfold into the reality we know. However, like many of the theories we've explored, the holographic principle is not without its challenges. While it offers a compelling framework for understanding the universe, it remains largely theoretical, with much of its evidence coming from mathematical models rather than direct observation. Additionally, the idea that our three-dimensional reality is a projection from a two-dimensional surface is difficult to reconcile with our everyday experience, making it a hard concept to fully grasp. Yet, the holographic principle continues to captivate scientists and thinkers alike, offering a radical new perspective on the nature of existence. It invites us to consider that the universe might be far stranger and more interconnected than we ever imagined, with the Big Bang serving as the moment when the cosmic hologram was first illuminated. As we ponder this mind-bending theory, we're reminded that the universe is a place of infinite mystery, where even the most fundamental aspects of reality may be far more complex and far more beautiful than we ever dreamed. Now, as we venture deeper into the holographic universe, let's explore the fascinating role of information theory in shaping this groundbreaking concept. At its core, information theory examines how information is stored, processed, and transmitted, and when applied to the holographic principle, it suggests that the very fabric of reality might be built on a foundation of information. Imagine the universe as a vast, intricate computer, where every particle, every force, and every event is encoded as bits of data. In this view, the Big Bang wasn't just the birth of matter and energy. It was the moment when the universe's information began to unfold into the reality we experience today. This idea challenges the traditional framework of physics, which has long focused on matter and energy as the building blocks of the cosmos. Instead, the holographic principle proposes that information is the fundamental currency of the universe. Think of it like this: just as a movie on a DVD is stored as a series of ones and zeros, the universe might be encoded on a two-dimensional surface, with the three-dimensional world we see being a projection of that data. This shift in perspective forces us to rethink what we consider real. If information is the foundation of reality, then space, time, and even gravity could be emergent properties, side effects of the way information is processed and displayed. One of the most intriguing aspects of this theory is how it bridges the gap between quantum mechanics and general relativity, two pillars of modern physics that have long resisted unification. Quantum mechanics deals with the behavior of particles at the smallest scales, while general relativity explains the large-scale structure of the cosmos. The holographic principle, rooted in information theory, offers a potential framework to connect these two realms. By treating the universe as a system of information, it provides a new way to understand phenomena like black holes, where quantum effects and gravitational forces collide in mysterious ways. But what does this mean for the origins of the universe? If the Big Bang was the moment when the universe's information began to project into 3 dimensions, it raises profound questions about what existed before. Was there a pre-existing code that defined the rules of our reality? Could the universe be part of a larger informational system, with the Big Bang marking the start of a specific program or simulation? These questions push the boundaries of both science and philosophy, inviting us to consider that the universe might be far more complex and far more interconnected than we ever imagined. Of course, the holographic principle is not without its skeptics. While it offers a compelling framework, it remains largely theoretical, with much of its evidence coming from mathematical models rather than direct observation. Critics argue that the idea of a holographic universe is difficult to test experimentally, and some question whether it truly simplifies our understanding of reality or merely shifts the complexity to a different level. Yet, even as debates continue, the holographic principle has undeniably reshaped how we think about the cosmos, offering a radical new lens through which to view the universe's origins and structure. As we reflect on the role of information theory in the holographic universe, we're reminded that the quest to understand the Big Bang is as much about unraveling the nature of reality as it is about exploring the past. This theory invites us to see the universe not as a collection of objects and forces, but as a dynamic, interconnected system of information, a cosmic code waiting to be deciphered. And as we continue to probe the mysteries of the cosmos, we may find that the answers lie not in the stars themselves, but in the data that defines them. Now, shifting our gaze to a theory that feels like it's straight out of a science fiction novel, let's explore the idea that the Big Bang was not a natural event, but the beginning of a simulated universe. This is the simulation hypothesis, a concept that suggests our entire reality might be an artificial construct, a kind of cosmic computer program. Imagine, for a moment, that the universe is akin to a highly advanced video game, with the Big Bang serving as the moment the simulation was booted up. In this view, everything we experience, stars, planets, life, even consciousness, could be the result of lines of code running on some unimaginably powerful computer. The roots of this idea stretch back to ancient philosophy, with thinkers like Plato pondering whether reality is merely a shadow of a deeper truth. But in modern times, the simulation hypothesis has gained traction thanks to advancements in technology and computing. If we can create virtual worlds that feel increasingly real, why couldn't a more advanced civilization, or even a future version of humanity, create a simulation so detailed that its inhabitants believe it's real. This line of thinking leads to the startling possibility that the Big Bang wasn't the birth of a natural universe, but the activation of a programmed one. From a scientific perspective, the simulation hypothesis raises fascinating questions. For instance, if the universe is a simulation, it might have certain rules or limitations built into its code. Some researchers have even proposed ways to test this idea, such as looking for glitches or patterns in the fabric of reality that could hint at an underlying program. One example is the idea that space and time might be pixelated at the smallest scales, much like how a digital image breaks down into individual pixels when you zoom in far enough. If such a structure were discovered, it could be evidence that our universe is, in fact, a simulation. But the simulation hypothesis isn't just a scientific curiosity, it's also a deeply philosophical idea. If our reality is a simulation, what does that mean for concepts like free will, purpose, and the nature of existence? Are we merely characters in someone else's story, or do we still have agency within the confines of the program? These questions challenge our understanding of what it means to be real and force us to confront the possibility that the universe might be far stranger than we ever imagined. Of course, not everyone is convinced. Critics argue that the simulation hypothesis is untestable, and in some ways, unfalsifiable, meaning it's impossible to prove wrong. Others point out that even if the universe is a simulation, it doesn't necessarily change how we experience reality. After all, whether the stars above are made of matter or lines of code, they still inspire awe and wonder. Still, the idea continues to captivate scientists, philosophers, and dreamers alike, offering a radical new perspective on the origins of the cosmos. As we ponder the possibility that the Big Bang was the start of a simulated universe, we're reminded that the quest to understand our origins is as much about exploring the nature of reality as it is about uncovering the past. This theory invites us to consider that the universe might not just be a physical construct, but a carefully designed experience, one that challenges us to question everything we think we know. And as we continue to probe the mysteries of existence, we may find that the answers lie not in the stars, but in the code that defines them. Now, as we delve deeper into the simulation hypothesis, let's examine the intriguing evidence that some scientists believe could point to our universe being a carefully crafted program. One of the most compelling arguments comes from the precision of mathematical constants. These are the fundamental numbers that govern the laws of physics, like the speed of light or the gravitational constant. What's fascinating is that these constants appear to be fine-tuned to an extraordinary degree. If even one of them were slightly different, life as we know it might not exist. Some theorists argue that this fine-tuning could be evidence of a programmed universe, where these values were deliberately set to allow for complexity and life to emerge. Another piece of potential evidence lies in the strange behavior of quantum mechanics. At the smallest scales, particles don't behave in predictable ways. Instead, they exist in a state of probability until observed. This has led some to suggest that the universe might be rendering reality only when it's being observed, much like how a video game only renders the parts of the world that a player is actively looking at. This idea, known as the observer effect, raises the possibility that our universe operates on a kind of computational framework, where resources are allocated efficiently to maintain the illusion of a seamless reality. Then there's the concept of pixelation at the smallest scales. Just as a digital image breaks down into pixels when zoomed in, some physicists speculate that space and time might have a fundamental limit to how finely they can be divided. If researchers were to discover such a limit, often referred to as the Planck scale, it could hint at a universe built on a grid-like structure, much like a simulation. While this remains speculative, it's a tantalizing idea that challenges our understanding of the fabric of reality. But what does all this mean for us? If the universe is a simulation, it forces us to reconsider fundamental concepts like free will and the nature of existence. Are our choices truly our own, or are they predetermined by the code of the simulation? Some argue that even within a simulated reality, free will could still exist if the program allows for genuine decision-making. Others suggest that our sense of agency might be an illusion, a byproduct of the simulation's design. These questions blur the line between science and philosophy, inviting us to rethink what it means to be conscious beings in a potentially artificial world. Critics, of course, remain skeptical. They point out that much of the evidence for a simulated universe is circumstantial and open to interpretation. After all, the fine-tuning of constants could simply be a result of the multiverse, where countless universes exist with different laws, and we happen to live in one that supports life. Similarly, quantum anomalies might just be quirks of nature that we don't yet fully understand. And while the idea of a pixelated universe is intriguing, it remains purely theoretical, with no concrete proof to support it. Yet, despite the skepticism, the simulation hypothesis continues to captivate our imagination. It challenges us to think beyond the boundaries of traditional science and consider the possibility that reality might be far more malleable and mysterious than we ever imagined. Whether or not the universe is a simulation, the very act of questioning its nature pushes us to explore the deepest corners of existence, reminding us that the search for truth is as much about the journey as it is about the destination. And as we continue to probe the mysteries of the cosmos, we may find that the answers lie not in the stars, but in the code that defines them. Now, shifting our gaze to a theory that bridges the ancient and the modern, let's explore the idea that the Big Bang was a cosmic egg. This concept, rooted in mythology and philosophy, suggests that the universe began as a primordial egg, a single point of potential that cracked open to release all of existence. Across cultures, from ancient Egypt to Hindu cosmology, the cosmic egg has been a powerful symbol of creation, representing the birth of order from chaos. It's a poetic and profound image, one that resonates surprisingly well with modern scientific theories about the Big Bang. In many ways, the cosmic egg mirrors the scientific description of the Big Bang. Just as the egg contains the potential for life within its shell, the singularity at the start of the Big Bang held the seeds of the entire universe, space, time, matter, and energy. When the egg cracks or the singularity expands, it gives rise to the cosmos as we know it. This parallel between myth and science is striking, suggesting that ancient cultures may have intuited truths about the universe's origins long before the advent of modern cosmology. The symbolism of the cosmic egg also aligns with the idea of symmetry breaking, a key concept in physics. In the early moments of the Big Bang, the universe was perfectly symmetrical, with all forces unified. But as it expanded and cooled, this symmetry broke, giving rise to the distinct forces and particles that shape our reality today. This process can be likened to the cracking of the egg, where a single, unified state gives way to diversity and complexity. It's a beautiful metaphor that captures both the unity and the diversity of the cosmos. But the cosmic egg theory isn't just about symbolism. It also offers a unique perspective on the nature of the universe's birth. Unlike some theories that suggest the Big Bang was a random or accidental event, the cosmic egg implies a sense of purpose or design. It suggests that the universe was born with an inherent potential, a blueprint for the complexity and beauty we see today. This idea resonates with those who see the universe as more than just a collection of particles and forces, but as a living, evolving entity with its own story to tell. Of course, the cosmic egg theory is not without its critics. Some argue that it's too metaphorical to be taken seriously as a scientific explanation. Others point out that while the parallels between myth and science are intriguing, they don't provide concrete evidence for how the universe began. Yet, even if the cosmic egg remains more of a philosophical concept than a scientific one, it invites us to think about the Big Bang in a new light, not just as a physical event, but as a moment of profound transformation and creation. As we reflect on this ancient yet timeless idea, we're reminded that the search for the universe's origins is as much about storytelling as it is about science. The cosmic egg reminds us that the Big Bang isn't just a moment in time. It's the beginning of a cosmic narrative, one that continues to unfold with every star that forms, every galaxy that spins, and every life that emerges. And as we explore the mysteries of the cosmos, we may find that the answers lie not just in equations and data, but in the stories we tell about the universe and our place within it. Now, as we delve deeper into the cosmic egg theory, let's explore how this ancient concept weaves together the threads of mythology and modern science. Across civilizations, from the ancient Egyptians to the Hindu sages, the cosmic egg has been a recurring symbol of creation, representing the birth of order from chaos. These myths, though separated by time and geography, share a striking similarity, a belief that the universe emerged from a single, unified source. This universal imagery suggests that humanity has long been fascinated by the idea of a singular beginning, a moment when everything we know came into being. In ancient Egyptian mythology, the cosmic egg is linked to the god Atum, who emerged from the primordial waters of chaos to create the world. Similarly, in Hindu cosmology, the Hiranyagarbha, or golden egg, is described as the source of all creation, containing the potential for the entire universe within its shell. These stories, though steeped in symbolism, echo the modern scientific understanding of the Big Bang, a singular event that gave rise to space, time, and matter. It's fascinating to see how these ancient narratives, crafted long before the advent of telescopes and particle accelerators, seem to mirror the scientific quest to understand the universe's origins. But the cosmic egg isn't just a relic of the past. It also offers a unique lens through which to view modern cosmology. The idea of a primordial egg aligns with the concept of a singularity, a point of infinite density and temperature from which the universe expanded. Just as the egg contains the potential for life, the singularity held the seeds of galaxies, stars, and planets. This parallel between myth and science invites us to consider whether ancient cultures, through intuition and observation, grasped truths about the cosmos that we are only now beginning to uncover through rigorous scientific inquiry. Moreover, the cosmic egg theory highlights the universality of human curiosity. Whether through myth or science, we've always sought to answer the same fundamental questions. Where did we come from? How did the universe begin? These questions transcend cultural boundaries, uniting us in a shared quest for understanding. The cosmic egg, as both a mythological symbol and a scientific metaphor, reminds us that the search for the universe's origins is a deeply human endeavor, one that connects us to our ancestors and to each other. Yet, while the cosmic egg offers a compelling bridge between myth and science, it also raises important questions about the nature of knowledge itself. Can ancient myths, rich in symbolism and metaphor, truly inform our scientific understanding of the universe? Or are they simply poetic expressions of humanity's awe and wonder? The answer may lie somewhere in between. While myths may not provide concrete evidence for the Big Bang, they offer a way of thinking about the universe that complements scientific inquiry. They remind us that the cosmos is not just a collection of particles and forces, but a story, one that we are still trying to understand. As we reflect on the cosmic egg's enduring legacy, we're reminded that the universe's origins are as much a matter of imagination as they are of calculation. The cosmic egg invites us to see the Big Bang not just as a physical event, but as a moment of profound transformation, a cracking open of possibilities that continues to shape our understanding of the cosmos. And as we explore the mysteries of the universe, we may find that the answers lie not just in the stars, but in the stories we tell about them. Now, shifting our gaze to a different cosmic perspective, let's explore the intriguing theory that the Big Bang was not just an explosive event, but a phase transition, a transformation akin to water freezing into ice. This idea reimagines the birth of the universe as a dramatic shift in the fundamental state of existence, much like how matter changes form under specific conditions. Imagine the early universe as a seething, chaotic soup of energy and particles, existing in a state of extreme heat and density. According to this theory, the Big Bang marked the moment when this primordial soup underwent a sudden and profound change, transitioning from one phase to another. Just as water molecules rearrange themselves into a crystalline structure when they freeze, the universe's fundamental forces and particles may have realigned during this cosmic phase transition, giving rise to the structure and order we observe today. This theory draws a fascinating parallel between the behavior of matter in everyday life and the grandest scales of the cosmos. In physics, Phase transitions are well understood phenomena. Think of steam condensing into water or liquid metal solidifying into a solid. These transitions often involve a release of energy and a reorganization of particles, and the same principles could apply to the early universe. The Big Bang, in this view, was not just an explosion, but a moment of cosmic reorganization, where the universe's fundamental properties shifted dramatically, leading to the rapid expansion and cooling we associate with its birth. One of the most compelling aspects of this theory is how it explains the uniformity of the universe. During a phase transition, systems often reach a state of equilibrium, where energy and matter are evenly distributed. This could account for the remarkably consistent temperature and density of the cosmic microwave background radiation, the faint afterglow of the Big Bang. Just as ice forms uniformly under the right conditions, the universe may have achieved a similar uniformity during its phase transition, setting the stage for the formation of galaxies, stars, and planets. But what triggered this cosmic phase transition? Some scientists suggest it could have been a phenomenon known as symmetry breaking. In the early universe, the fundamental forces gravity, electromagnetism, and the strong and weak nuclear forces may have been unified into a single, all-encompassing force. As the universe cooled, this symmetry broke, causing the forces to separate and take on their distinct identities. This breaking of symmetry could have been the catalyst for the phase transition, releasing immense energy and driving the universe's rapid expansion. The phase transition theory also offers a fresh perspective on the universe's evolution. Just as water can exist in multiple phases, solid, liquid, and gas, the universe may have undergone multiple transitions throughout its history. This idea opens the door to the possibility of other cosmic phase transitions, perhaps even in the future, that could reshape the universe in ways we can scarcely imagine. As we ponder this theory, we're reminded of the elegance and simplicity of nature's processes. Whether it's water freezing into ice or the universe transitioning from chaos to order, the underlying principles remain the same. The phase transition theory invites us to see the Big Bang not as a singular, isolated event, but as part of a larger, ongoing process, a cosmic dance of transformation that continues to shape the fabric of reality. And as we explore these ideas, we may find that the universe's origins are not just a story of creation, but a tale of endless change and possibility. Now, as we venture deeper into the cosmic tapestry, let's unravel the pivotal role of symmetry breaking in the Big Bang. This concept, rooted in the heart of particle physics, offers a profound explanation for how the universe transitioned from a state of perfect uniformity to the rich complexity we see today. Symmetry breaking is like a cosmic switch, a moment when the universe's fundamental forces and particles shifted from a unified, symmetrical state to a fractured, diverse one, setting the stage for everything that followed. In the earliest moments of the universe, all four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, may have been indistinguishable, woven together into a single, seamless fabric. This state of perfect symmetry is often compared to a calm, featureless ocean, where no wave or current stands out. But as the universe expanded and cooled, this symmetry began to break. Imagine the ocean suddenly developing distinct currents, whirlpools, and waves. In the same way, the unified force split into the distinct forces we recognize today, each with its own unique properties and behaviors. This breaking of symmetry wasn't just a minor adjustment, it was a cosmic upheaval. As the forces separated, they released an enormous amount of energy, driving the rapid expansion of the universe. This process, known as inflation, explains why the universe is so vast and uniform on large scales. It's as if the symmetry breaking acted like a cosmic bellows, blowing up the universe to its current size in a fraction of a second. Without this event, the universe might have remained a dense, chaotic soup, never giving rise to the galaxies, stars, and planets we know. But symmetry breaking didn't just shape the universe's expansion, it also laid the groundwork for the structure of matter itself. As the forces separated, particles began to take on distinct identities. Quarks, electrons, and other fundamental particles emerged, each governed by the newly distinct forces. This differentiation allowed matter to clump together, forming atoms, molecules, and eventually, the building blocks of stars and galaxies. In this way, symmetry breaking wasn't just a moment of cosmic change, it was the birth of complexity itself. The implications of symmetry breaking extend far beyond the Big Bang. In particle physics, this concept helps explain why certain particles have mass while others don't. The Higgs field, for example, is thought to have emerged during symmetry breaking, giving mass to particles like electrons and quarks. Without this process, the universe would be a very different place, devoid of the stable structures that make life possible. Symmetry breaking also offers a tantalizing glimpse into the universe's future. Some theories suggest that the universe could undergo further symmetry breaking events, leading to new phases of existence. Just as the early universe transitioned from a state of perfect symmetry to one of diversity, future transitions could reshape the cosmos in ways we can't yet imagine. These possibilities remind us that the universe is not a static entity, but a dynamic, ever-evolving system, shaped by the interplay of forces and particles. As we reflect on the role of symmetry breaking, we're reminded of the delicate balance that underpins the cosmos. From the tiniest particles to the vast expanse of space, the universe's structure is a testament to the power of transformation. Symmetry breaking not only explains the origins of the universe, but also invites us to ponder its future, a future filled with endless possibilities and uncharted horizons. And as we continue to explore these ideas, we may find that the universe's story is far from over, but rather a tale of perpetual change and discovery. Now, shifting our gaze to an even grander cosmic perspective, let's explore the idea that the Big Bang was not a singular, isolated event, but one of countless occurrences within a multiverse. This theory, known as the multiverse hypothesis, suggests that our universe is just one of many, perhaps an infinite number, of universes, each with its own unique set of physical laws and properties. Imagine a vast cosmic tapestry where each thread represents a separate universe, woven together in an intricate, ever-expanding fabric of existence. The multiverse theory challenges the traditional notion of a single, unique universe by proposing that the Big Bang was merely one event in an endless series of cosmic births. In this view, the universe we inhabit is just one bubble in a frothy sea of universes, each born from its own Big Bang. This idea stems from the concept of eternal inflation, where space-time expands exponentially, creating pockets that develop into separate universes. It's as if the cosmos is a bubbling pot of water, with each bubble representing a new universe, each one potentially different from the last. But what does this mean for our understanding of the universe? For one, it raises profound questions about the nature of reality. If there are countless universes, each with its own laws of physics, then the conditions we observe in our universe, such as the precise values of fundamental constants, might not be unique. Instead, they could be just one possible outcome among an infinite array of possibilities. This idea challenges the notion that our universe is finely tuned for life, suggesting instead that life exists here simply because, in a multiverse, every possible scenario is bound to occur somewhere. The multiverse theory also has significant implications for cosmology. If other universes exist, they might be entirely different from ours, with different dimensions, forces, and particles. Some could be barren and lifeless, while others might teem with forms of existence we can't even imagine. This idea pushes the boundaries of scientific inquiry, forcing us to reconsider what we know about the origins and nature of the cosmos. It's a humbling reminder that our universe, vast as it is, might be just a small part of an even greater reality. Yet, the multiverse hypothesis is not without its challenges. One of the biggest hurdles is the question of evidence. Since other universes, by definition, exist beyond the observable limits of our own, how can we ever confirm their existence? Some scientists point to anomalies in the cosmic microwave background radiation, the afterglow of the Big Bang, as potential clues. Others suggest that collisions between universes might leave detectable imprints in the fabric of space-time. While these ideas remain speculative, they offer tantalizing possibilities for future discoveries. As we ponder the multiverse, we're confronted with both awe and uncertainty. The idea that our universe is just one of many invites us to rethink our place in the cosmos. It challenges us to consider that the story of existence might be far more complex and interconnected than we ever imagined. And while the multiverse remains a theory, it serves as a powerful reminder of the boundless mysteries that await us in the ever-expanding tapestry of reality. With each new discovery, we inch closer to understanding not just our universe, but the infinite possibilities that lie beyond. Now, as we delve deeper into the multiverse hypothesis, let's examine the scientific evidence that lends credibility to the idea of parallel universes. One of the most compelling pieces of evidence comes from the concept of cosmic inflation. This theory suggests that in the earliest moments of the universe, space-time expanded at an unimaginable rate, far faster than the speed of light. This rapid expansion could have created bubbles of space-time, each developing into its own separate universe. The cosmic microwave background radiation, often referred to as the afterglow of the Big Bang, shows subtle patterns that some scientists interpret as potential fingerprints of these bubble universes colliding or interacting in the early cosmos. Quantum mechanics also offers intriguing support for the multiverse theory. In the quantum world, particles exist in a state of probability until they are observed. This has led to the idea of the many worlds interpretation, which proposes that every possible outcome of a quantum event actually occurs, but in separate, branching universes. For example, if you flip a coin, in one universe it lands heads, while in another it lands tails. While this interpretation is controversial, it provides a fascinating framework for understanding how an infinite number of universes could exist, each representing a different outcome of every possible event. Another line of evidence comes from the fine-tuning of the universe's physical constants. The values of these constants, such as the strength of gravity or the charge of an electron, seem perfectly calibrated to allow for the existence of life. Some scientists argue that this fine-tuning is evidence of a multiverse, where countless universes exist with different constants, and we simply inhabit the one where conditions are just right for life to emerge. This idea shifts the question from why is our universe so finely tuned to what are the odds that in an infinite multiverse, at least one universe would have the right conditions. The multiverse theory also has profound philosophical implications. It challenges our understanding of uniqueness and purpose. If there are infinite universes, each with its own set of physical laws, then the idea of a single, special universe designed for life becomes less compelling. Instead, life might be a statistical inevitability in a cosmos teeming with possibilities. This perspective invites us to rethink not only our place in the universe, but also the very nature of existence itself. Scientifically, the multiverse hypothesis pushes the boundaries of what we can observe and test, since other universes, by definition, lie beyond our observable horizon. Confirming their existence directly is a significant challenge. However, indirect evidence, such as anomalies in the cosmic microwave background or unexpected patterns in particle physics, could provide clues. Some researchers are even exploring the possibility of detecting gravitational waves from other universes, which might leave faint imprints in our own. As we consider the evidence for parallel universes, we're reminded of the vastness of the unknown. The multiverse theory invites us to imagine a reality far grander and more complex than we've ever conceived. It challenges us to question not just the nature of our universe, but the very fabric of existence. And while the search for evidence continues, the multiverse remains a captivating idea that expands our understanding of the cosmos and our place within it. Now, as we shift our gaze to the horizon of cosmic possibilities, let's explore the intriguing idea that the Big Bang might not have been a singular event, but rather the beginning of an endless cycle, a time loop. This theory suggests that the universe doesn't just expand and fade away, but instead collapses and reboots in an infinite loop, with each cycle beginning anew with a Big Bang. It's a concept that challenges our linear understanding of time and invites us to imagine a cosmos that repeats itself endlessly. At the heart of this theory lies the concept of entropy, a measure of disorder in the universe. According to the second law of thermodynamics, entropy always increases over time, driving the universe toward a state of maximum disorder. But what if at some point this process reverses? Some scientists propose that the universe could reach a state where entropy resets, causing everything to collapse back into a singularity, only to explode outward again in a new Big Bang. This cyclical model suggests that time itself might loop, with each cycle of expansion and contraction marking a new chapter in the universe's story. The arrow of time, which points from the past to the future, is another key element in this theory. In our everyday experience, time flows in one direction. We remember the past but not the future. However, in a time loop universe, the arrow of time could bend, creating a closed loop where the end of one cycle becomes the beginning of the next. This would mean that the Big Bang isn't just the start of our universe, but also the endpoint of a previous cycle, creating a cosmic rhythm that repeats indefinitely. This idea also ties into the concept of closed time-like curves, hypothetical paths through space-time that loop back on themselves. If such curves exist, they could allow events to repeat in an endless cycle, supporting the idea of a time loop universe. While this remains speculative, it offers a fascinating way to think about the nature of time and the universe's ultimate fate. The implications of a time loop universe are profound. It suggests that the cosmos is not a one-time event, but an eternal dance of creation and destruction. It also raises questions about the nature of existence. If the universe repeats itself, does that mean history repeats as well? Could the same stars, planets, and even life forms emerge in each cycle, or would each iteration be unique? These questions push the boundaries of our understanding and invite us to rethink the very fabric of reality. As we ponder the possibility of a time loop universe, we're reminded of the cyclical nature of many natural processes, seasons changing, stars being born and dying, and even the rhythms of life itself. This theory offers a poetic vision of the cosmos, one where beginnings and endings are intertwined in an eternal cycle. And while the evidence for such a universe remains elusive, the idea continues to inspire curiosity and wonder, challenging us to imagine a reality where time itself is not a straight line, but a never-ending loop. Now, as we venture deeper into the mysteries of time and space, let's explore the fascinating role of closed time-like curves in shaping the idea of a cyclical universe. These hypothetical pathways through space-time, which loop back on themselves, offer a compelling framework for understanding how the universe might repeat itself in an endless cycle. Imagine a cosmic track where time doesn't flow in a straight line, but instead curves back, creating a loop where the end of one cycle becomes the start of another. This concept, while speculative, opens up a world of possibilities for rethinking the nature of time and the universe's ultimate fate. Closed time-like curves are rooted in the equations of general relativity, which describe how massive objects warp space-time. In certain extreme conditions, such as near a rotating black hole or in the presence of exotic matter, these curves could theoretically form, allowing time to loop back on itself. If such curves exist, they could provide a mechanism for the universe to reset, with each Big Bang marking the beginning of a new cycle. This idea aligns with the notion of a time loop universe, where the cosmos endlessly repeats its journey of expansion and contraction. However, the existence of closed time-like curves is not without its challenges. One major hurdle is the potential for paradoxes, such as the famous grandfather paradox, where traveling back in time could lead to contradictions. If time loops exist, could someone alter the past in a way that disrupts the future? While these paradoxes are intriguing, they also highlight the complexities of reconciling such theories with our current understanding of physics. Scientists continue to debate whether these curves are physically possible or merely mathematical curiosities. Another challenge lies in the nature of entropy, which we discussed earlier. If the universe is cyclical, how does entropy reset with each new cycle? Some theories suggest that entropy could be recycled in some way, allowing the universe to return to a low entropy state at the start of each cycle. Others propose that the laws of physics might behave differently in a closed time-like curve, enabling the universe to reset without violating thermodynamic principles. These ideas remain speculative, but they offer tantalizing possibilities for understanding the universe's cyclical nature. Despite the challenges, the concept of closed time-like curves continues to inspire both scientific inquiry and imaginative speculation. They offer a way to envision a universe where time is not a one-way street, but a looping, interconnected web. This perspective challenges our linear understanding of time and invites us to consider a cosmos where beginnings and endings are not fixed, but part of an eternal rhythm. As we reflect on the role of closed time-like curves in a cyclical universe, we're reminded of the profound questions they raise about the nature of reality. Could the universe truly be a never-ending loop, with each cycle bringing new possibilities? Or are these curves simply a fascinating thought experiment, pushing the boundaries of our imagination? While the answers remain elusive, the exploration of these ideas continues to spark curiosity and wonder, inviting us to rethink the very fabric of time and space. Now shifting our gaze to the quantum realm, let's explore the intriguing idea that the Big Bang might have been a quantum tunneling event. This theory suggests that our universe could have emerged from a pre-existing state through a process rooted in the strange and unpredictable world of quantum mechanics. Quantum tunneling is a phenomenon where particles can pass through barriers that, according to classical physics, should be impossible to overcome. It's as if a ball could magically appear on the other side of a wall without ever going over it. In the context of the Big Bang, this concept takes on a cosmic scale, proposing that the universe itself could have tunneled into existence from a prior state of nothingness or a different form of reality. At the heart of this theory lies the principle of quantum uncertainty, which states that particles can exist in multiple states simultaneously until they are observed or measured. This uncertainty allows for the possibility of spontaneous fluctuations in energy, even in what we might consider empty space. In the early moments of the universe, a quantum fluctuation could have triggered a tunneling event, causing a rapid expansion of space and time, what we now call the Big Bang. This idea challenges the traditional notion of a singular, explosive beginning, instead suggesting a more subtle and probabilistic origin. The role of quantum mechanics in this theory is profound. It shifts our understanding of the universe's birth from a deterministic event to one governed by probability and chance. If the Big Bang was a quantum tunneling event, It implies that the universe's creation was not a unique or inevitable occurrence, but rather one of many possible outcomes. This perspective aligns with the broader principles of quantum theory, where reality is shaped by probabilities rather than certainties. It also raises fascinating questions about the nature of existence itself. Could there be other universes that emerged from similar tunneling events, each with its own set of physical laws and constants? However, this theory is not without its challenges. One major question is how a quantum fluctuation could produce something as vast and complex as our universe. While quantum tunneling is well documented on the scale of particles, scaling it up to the size of the cosmos requires a leap of imagination and a deeper understanding of quantum gravity, a field that remains largely theoretical. Additionally, the idea of a pre-existing state raises questions about what existed before the Big Bang. Was it a void, a different universe, or something entirely beyond our comprehension? These questions push the boundaries of both physics and philosophy, inviting us to rethink the very nature of reality. Despite these uncertainties, the quantum tunneling theory offers a compelling alternative to traditional Big Bang models. It bridges the gap between the microscopic world of quantum mechanics and the macroscopic scale of the cosmos, suggesting that the universe's origins might be far more intricate and interconnected than we once thought. As we continue to explore this idea, we're reminded of the profound mysteries that still surround the birth of our universe and the endless possibilities that lie within the quantum realm. Now, let's delve deeper into the quantum vacuum, a concept that plays a pivotal role in the quantum tunneling theory of the Big Bang. The quantum vacuum is not empty space, as we might imagine it. Instead, it's a seething, dynamic field, teeming with virtual particles that pop in and out of existence in fleeting moments. These particles are a direct consequence of the uncertainty principle in quantum mechanics, which allows energy to fluctuate even in what appears to be a void. This constant activity means that the quantum vacuum is far from inert. It's a bubbling cauldron of potential, where the seeds of the universe could have been sown. In the context of the Big Bang, the quantum vacuum serves as the stage upon which the drama of creation unfolded. Imagine it as a cosmic canvas, where a sudden fluctuation in energy could have triggered the birth of our universe. This fluctuation wouldn't need to come from anywhere external. It could arise spontaneously from the vacuum itself, thanks to the inherent unpredictability of quantum mechanics. This idea suggests that the universe didn't emerge from nothing in the traditional sense, but rather from a state of quantum potential, where the rules of physics as we know them were just beginning to take shape. One of the most fascinating aspects of the quantum vacuum is its connection to dark energy, the mysterious force driving the accelerated expansion of the universe. Dark energy is often described as a property of space itself, and some theories propose that it could be linked to the energy of the quantum vacuum. If this is true, then the same quantum processes that may have sparked the Big Bang could still be at work today, shaping the fate of the cosmos. This connection raises profound questions about the nature of dark energy and whether it's a remnant of the universe's earliest moments. The quantum vacuum also offers a potential explanation for the uniformity of the universe. In the moments following the Big Bang, the universe expanded at an astonishing rate, a process known as inflation. This rapid expansion could have been driven by the energy of the quantum vacuum, smoothing out irregularities and creating the remarkably even distribution of matter and energy we observe today. In this way, the quantum vacuum doesn't just explain the origin of the universe, it also helps us understand its large-scale structure. However, the quantum vacuum theory is not without its challenges. One major question is how such a delicate quantum process could give rise to something as vast and complex as the universe. While quantum fluctuations are well documented on the smallest scales, scaling them up to cosmic proportions requires a leap of imagination and a deeper understanding of quantum gravity. Additionally, the idea of a quantum vacuum raises philosophical questions about the nature of existence. If the universe emerged from a state of quantum potential, what does that say about the nature of reality itself? Are we living in a universe that is, at its core, probabilistic rather than deterministic? Despite these uncertainties, the quantum vacuum theory provides a compelling framework for understanding the Big Bang. It bridges the gap between the microscopic world of quantum mechanics and the macroscopic scale of the cosmos, suggesting that the universe's origins might be far more intricate and interconnected than we once thought. As we continue to explore this idea, we're reminded of the profound mysteries that still surround the birth of our universe and the endless possibilities that lie within the quantum realm. Now, shifting our gaze to a theory that reimagines the Big Bang as a cosmic rebirth, we explore the idea that the universe's birth was not a singular event, but part of an endless cycle of collapse and renewal. This concept, known as the cosmic rebound theory, suggests that the Big Bang was not the beginning of everything, but rather the result of a previous universe, collapsing in on itself, and then rebounding in a spectacular explosion of energy and matter. It's a vision of the cosmos that paints the universe as a phoenix, rising from its own ashes in an eternal dance of destruction and creation. At the heart of this theory lies the idea of a cyclic universe, where the cosmos undergoes endless cycles of expansion and contraction. Imagine a universe that expands to its limit, slows down, and then begins to collapse under the pull of gravity, eventually crunching down into an incredibly dense state. Instead of ending in a final, irreversible collapse, this dense state triggers a rebound, a new Big Bang that births a fresh universe, starting the cycle all over again. This process could repeat indefinitely, with each cycle lasting billions or even trillions of years. The cosmic rebound theory offers a fascinating alternative to the traditional view of the Big Bang as a one-time event. It suggests that our universe is just one chapter in an infinite cosmic story, with no true beginning or end. This idea aligns with certain interpretations of general relativity and quantum mechanics, which allow for the possibility of a universe that cycles through phases of expansion and contraction. It also provides a potential solution to the question of what came before the Big Bang. Instead of a mysterious singularity, there was simply another universe, collapsing and rebounding in an endless loop. One of the most intriguing aspects of this theory is how it connects to the concept of entropy, the measure of disorder in a system. In a cyclic universe, entropy would reset with each new cycle, allowing the universe to start fresh without the buildup of disorder that would otherwise make infinite cycles impossible. This idea challenges our understanding of time and the arrow of entropy, suggesting that the laws of physics might operate differently on a cosmic scale than they do within a single cycle. However, the cosmic rebound theory is not without its challenges. One major question is how a collapsing universe could rebound without violating the laws of physics as we know them. Some physicists propose that quantum effects could play a role, allowing the universe to bounce back from collapse in a way that classical physics cannot explain. Others suggest that the rebound might be driven by exotic forms of energy or matter that we have yet to discover. These possibilities highlight the speculative nature of the theory and the need for further exploration. Despite these uncertainties, the cosmic rebound theory offers a compelling vision of the universe as a dynamic, ever-changing entity. It invites us to think beyond the confines of a single Big Bang and consider the possibility that our universe is part of a much larger, more intricate cosmic tapestry. As we continue to explore this idea, we're reminded that the story of the universe is far from complete, and that the answers to its deepest mysteries might lie in the echoes of its past cycles. Now, as we delve deeper into the cosmic rebound theory, let's examine the evidence that lends credibility to the idea of a cyclic universe. One of the most compelling pieces of support comes from the cosmic microwave background radiation, the faint afterglow of the Big Bang. This ancient light, which permeates the universe, holds subtle clues about the cosmos's origins and evolution. Scientists have discovered anomalies in this radiation patterns and irregularities that don't quite fit the standard model of a single Big Bang event. Some researchers suggest these anomalies could be echoes of a previous universe, imprinted on the fabric of space-time during a prior cycle of collapse and rebound. Another intriguing piece of evidence comes from the study of dark energy, the mysterious force driving the universe's accelerated expansion. In a cyclic universe, dark energy could play a crucial role in determining how one cycle transitions to the next. Some models propose that dark energy weakens over time, allowing gravity to eventually halt the expansion and trigger a collapse. This interplay between dark energy and gravity could create the conditions necessary for a cosmic rebound, setting the stage for a new universe to emerge. While this remains speculative, it offers a tantalizing framework for understanding the universe's cyclical nature. The cyclic universe theory also finds support in the mathematical elegance of certain cosmological models. For instance, the idea of a bounce rather than a singularity aligns with some interpretations of quantum gravity, which suggests that the extreme conditions of a collapsing universe could be governed by quantum effects. These effects might prevent the universe from reaching a true singularity, instead allowing it to rebound into a new phase of expansion. This concept not only avoids the paradoxes associated with singularities, but also provides a natural mechanism for the universe's renewal. Looking ahead, the implications of a cyclic universe are profound. If the cosmos undergoes endless cycles of birth, death, and rebirth, it challenges our understanding of time itself. Instead of a linear progression from a single beginning to an eventual end, time becomes a loop, with each cycle offering a fresh start. This raises fascinating questions about the fate of the universe. Will future cycles resemble our own, or will they give rise to entirely new laws of physics and forms of matter? The cyclic universe theory invites us to consider the possibility that our universe is just one iteration in an infinite sequence, each with its own unique story. As we ponder these ideas, it's worth noting that the cyclic universe theory is still a work in progress. While the evidence is intriguing, it remains inconclusive, and many questions remain unanswered. Yet, the theory's ability to address some of the most profound mysteries of cosmology, such as the nature of the Big Bang and the ultimate fate of the universe, makes it a compelling area of study. It reminds us that the cosmos is full of surprises, and that our quest to understand its origins is far from over. With each new discovery, we inch closer to unraveling the secrets of the universe's grand design. Now turning to a theory that bridges the realms of science and spirituality, let's explore the idea that the Big Bang was an act of divine creation. This perspective suggests that the universe's birth was not a random or purely physical event, but rather a deliberate act by a higher power. For many, this theory offers a way to reconcile the scientific understanding of the cosmos with deeply held religious or spiritual beliefs. It invites us to consider the possibility that the universe's origins are not just a matter of physics, but also of purpose and meaning. At the heart of this theory is the question of how science and religion can coexist in explaining the Big Bang. While science seeks to understand the mechanisms behind the universe's birth, such as quantum fluctuations or cosmic inflation, the divine creation theory introduces the idea of intentionality. It proposes that the laws of physics, the fine-tuning of the universe, and the emergence of life are not accidental, but part of a grand design. This perspective resonates with many who see the universe's complexity and order as evidence of a creator's hand. One of the most compelling aspects of this theory is its ability to address the why behind the Big Bang. Science excels at explaining the how, but it often leaves questions about purpose unanswered. The divine creation theory steps into this space, offering a narrative that gives the universe a sense of direction and significance. For instance, the precise conditions required for life to exist, often referred to as the fine-tuning problem, are seen by some as evidence of a purposeful act. The constants of nature, such as the strength of gravity or the charge of an electron, are so finely balanced that even slight changes would make life impossible. To proponents of this theory, this fine-tuning is not a coincidence, but a sign of intentional creation. However, this theory also raises profound philosophical questions. If the Big Bang was an act of divine creation, what does that imply about the nature of the Creator? Is the universe a one-time creation or part of an ongoing process? And how do we reconcile the existence of suffering and chaos in the world with the idea of a benevolent Creator? These questions have been debated for centuries, and they continue to challenge both religious and scientific thinkers. The divine creation theory doesn't provide easy answers, but it encourages us to think deeply about the relationship between the physical and the metaphysical. It's important to note that this theory doesn't necessarily conflict with scientific discoveries. Many scientists and theologians argue that science and religion can coexist, each offering different but complementary perspectives on the universe. For example, the Big Bang theory itself was initially met with resistance from some religious groups, but over time, many have come to see it as compatible with the idea of creation. The Big Bang could be viewed as the moment when a divine force set the universe in motion, with the laws of physics governing its subsequent evolution. As we reflect on this theory, it's clear that it offers more than just an explanation for the Big Bang. It invites us to consider the deeper questions of existence. Why is there something rather than nothing? What is the purpose of the universe? And what role do we, as conscious beings, play in this grand cosmic story? These questions may never have definitive answers, but they remind us that the search for understanding is as much about meaning as it is about facts. The divine creation theory challenges us to look beyond the physical and explore the spiritual dimensions of the cosmos, offering a perspective that is both humbling and inspiring. Now shifting our focus to the intricate dance between faith and science, let's explore how these two seemingly different realms intersect in our understanding of the Big Bang. While science provides us with tools to uncover the mechanics of the universe, faith often steps in to address the deeper questions of purpose and meaning. Together, they offer a more holistic view of the cosmos, one that embraces both the measurable and the mysterious. At the core of this relationship is the idea that faith and science are not adversaries, but partners in the quest for understanding. Science seeks to explain the how of the universe, its origins, its laws, and its evolution. Faith, on the other hand, often grapples with the why, the purpose behind existence, and the role of humanity within it. The divine creation theory bridges these two perspectives, suggesting that the Big Bang could be both a scientific event and a spiritual act. This duality invites us to see the universe not just as a collection of particles and forces, but as a story with intention and significance. One of the most fascinating aspects of this interplay is how it shapes our perception of the universe's origins. For many, the Big Bang is not just a moment of physical creation, but a profound expression of something greater. The precision of the universe's constants, the delicate balance required for life, and the sheer scale of existence all point to a reality that transcends pure chance. Faith offers a lens through which these observations can be interpreted as evidence of a guiding hand, while science provides the framework to study and understand the mechanisms at work. Together, they create a richer, more layered understanding of the cosmos. This collaboration between faith and science also challenges us to rethink the boundaries of knowledge. While science excels at explaining observable phenomena, it often encounters limits when dealing with questions that lie beyond the physical realm. Faith, with its focus on the intangible, steps into this space, offering insights that science alone cannot provide. For instance, the concept of a divine creator introduces the idea of intentionality, a universe designed with purpose. This perspective doesn't negate scientific discoveries, but complements them, suggesting that the laws of physics and the emergence of life are part of a larger, more meaningful narrative. However, this relationship is not without its tensions. The history of science and religion is marked by moments of conflict, as each has sought to assert its authority over the other. Yet, in recent years, there has been a growing recognition that these two domains can coexist and even enrich one another. Many scientists and theologians now argue that faith and science are not mutually exclusive, but different ways of engaging with the same reality. The Big Bang, for example, can be seen as both a scientific event and a moment of divine creation, depending on the perspective one adopts. As we consider the role of faith and science in understanding the Big Bang, it's clear that both offer valuable insights. Science gives us the tools to explore the universe's mechanics, while faith invites us to ponder its deeper meaning. Together, they provide a more complete picture of our origins, one that acknowledges both the physical and the spiritual dimensions of existence. This dual approach not only deepens our understanding of the cosmos, but also enriches our sense of connection to it, reminding us that the search for knowledge is as much about wonder as it is about discovery. Now shifting our gaze to a theory that turns the search for meaning on its head, let's explore the idea that the Big Bang was nothing more than a cosmic accident. This perspective suggests that the birth of our universe was not the result of a grand design or a deliberate act, but rather a random, chance event. It's a theory that challenges our deepest instincts to find purpose in the cosmos, forcing us to confront the possibility that the universe exists not because of intention, but in spite of it. At the heart of this theory lies the concept of probability. In an infinite expanse of possibilities, the Big Bang could simply have been one of countless random fluctuations in the fabric of existence. Imagine a vast ocean of potential, where universes bubble up and fade away like waves on the shore. In this view, our universe is just one of many, born not from purpose, but from the sheer randomness of quantum mechanics. This idea flips the script on traditional cosmology, suggesting that the universe's existence is not a miracle, but a statistical inevitability. This theory also raises profound questions about the nature of meaning itself. If the Big Bang was an accident, does that mean our existence is equally devoid of purpose? For some, this idea is unsettling, as it challenges the notion that life and the universe are part of a greater plan. Yet, for others, it offers a kind of liberation. If the universe is random, then meaning is not something we find, but something we create. It's a perspective that shifts the responsibility for purpose from the cosmos to ourselves, empowering us to define our own significance in an indifferent universe. From a scientific standpoint, the cosmic accident theory aligns with certain principles of quantum mechanics and cosmology. Quantum fluctuations, for instance, are random by nature, and they play a key role in the behavior of particles at the smallest scales. If such fluctuations can occur spontaneously, it's not a stretch to imagine that the Big Bang could have been the result of a similar process on a cosmic scale. This idea is further supported by the concept of the multiverse, where countless universes exist, each with its own set of physical laws and conditions. In this framework, our universe is just one of many, and its existence is no more remarkable than the roll of a cosmic die. However, this theory is not without its challenges. One of the biggest hurdles is explaining the fine-tuning of the universe, the precise conditions that allow for the existence of life. If the Big Bang was a random event, how did the universe end up with such a delicate balance of constants and forces? Some argue that this fine-tuning is evidence of design, while others suggest that it's simply a matter of probability. In a multiverse with infinite possibilities, it's statistically inevitable that at least one universe would have the right conditions for life. Our universe, in this view, is not special, it's just lucky. As we ponder the implications of the cosmic accident theory, it's clear that it challenges us to rethink our place in the universe. If the Big Bang was random, then our existence is not the result of a grand plan, but a fortunate coincidence. This idea can be both humbling and empowering, reminding us that while the universe may not care about us, we have the power to care about each other and the world we inhabit. It's a perspective that invites us to embrace the uncertainty of existence and find meaning not in the stars, but in the choices we make here on Earth. With this thought-provoking theory in mind, let's now turn to the role of probability in shaping the universe and how it might explain the Big Bang as a rare, random event. Now, as we delve deeper into the cosmic accident theory, let's explore the fascinating role of probability in shaping the universe. Probability, at its core, is the measure of how likely an event is to occur. In the context of the Big Bang, it suggests that our universe's birth was not a deliberate act, but rather the result of an incredibly rare, random fluctuation in the fabric of existence. To put it simply, the universe we know might just be a lucky roll of the cosmic dice. Imagine standing in front of a vast, infinite roulette wheel, where every spin represents the potential birth of a new universe. Most spins result in universes that collapse instantly or fail to sustain any form of complexity. But every once in a while, the wheel lands on the perfect combination, a universe with just the right conditions to allow stars, planets, and even life to form. Our universe, in this analogy, is that one in a trillion spin. It's not special because it was destined to be, but because it happened to be. This idea ties closely to the concept of the multiverse, where countless universes exist, each with its own unique set of physical laws and constants. In such a scenario, the odds of a universe like ours emerging are no longer astronomically low. They are inevitable. With an infinite number of universes, every possible configuration of physical laws becomes not just possible, but guaranteed. Our universe, with its finely tuned constants that allow for life, is simply one of the many possible outcomes in this cosmic lottery. But what does this mean for the existence of life? If the Big Bang was a random event, and our universe is just one of countless others, does that diminish the significance of life? Not necessarily. While it might suggest that life is not the result of a grand design, it also highlights the extraordinary rarity and preciousness of our existence. In a multiverse filled with lifeless, chaotic universes, the fact that we exist at all is a testament to the incredible odds we've overcome. It's a reminder that life, even if accidental, is a remarkable and fleeting phenomenon in the vastness of existence. From a scientific perspective, the role of probability in the Big Bang is supported by our understanding of quantum mechanics. At the smallest scales, particles behave unpredictably, popping in and out of existence in a dance governed by chance. If such randomness can occur at the quantum level, it's not unreasonable to imagine that the birth of the universe itself could have been a similar quantum fluctuation, amplified to cosmic proportions. This idea is further bolstered by the observation of cosmic inflation, the rapid expansion of the universe in its earliest moments, which could have been triggered by a random quantum event. However, this theory also raises questions about the fine-tuning of the universe. How did a random event produce a universe with such precise conditions for life? Some argue that this fine-tuning is evidence of a deeper, perhaps intentional, mechanism at work. Others suggest that in an infinite multiverse, fine-tuning is simply a matter of statistics. With enough universes, one was bound to get it right. This debate continues to challenge scientists and philosophers alike as they grapple with the implications of a universe born from chance. As we reflect on the role of probability in the Big Bang, it's clear that this theory invites us to embrace a new perspective on existence. It challenges us to find meaning not in the stars, but in the choices we make and the connections we forge. If the universe is random, then our lives are not part of a grand cosmic plan. They are what we make of them, and in that randomness, there is both freedom and responsibility. The universe may not care about us, but we have the power to care about each other and the world we share. With this thought in mind, let's now turn to another intriguing theory that reimagines the Big Bang as a cosmic rebound, a universe collapsing and expanding in an endless cycle of creation and destruction. As we bring our cosmic journey to a close, let's take a moment to reflect on the strange and fascinating theories we've explored about the Big Bang. From the idea of a black hole explosion in another universe to the possibility of a holographic projection or even a simulated reality, each theory challenges our understanding of the universe in profound ways. These ideas push the boundaries of science and philosophy, inviting us to question not just how the universe began, but what it means to exist at all. Theories like the cosmic egg, the multiverse, and the quantum fluctuation remind us that the Big Bang is far from a settled story. Instead, it's a puzzle with countless pieces, each offering a glimpse into the vast, mysterious nature of reality. Whether the universe was born from a collision of branes, a white hole event, or a random cosmic accident, these theories inspire us to keep asking questions and seeking answers. They remind us that curiosity is at the heart of what it means to be human. As we ponder these ideas, it's clear that the Big Bang is more than just a scientific concept. It's a gateway to endless possibilities. It challenges us to rethink our place in the cosmos and to embrace the wonder of the unknown. Whether you're drawn to the elegance of string theory, the mystery of the multiverse, or the philosophical implications of a simulated reality, one thing is certain: the universe is far stranger and more beautiful than we can imagine. So, what do you think? Which of these theories resonates with you the most? Do you believe the Big Bang was a cosmic accident, a divine creation, or something entirely beyond our current understanding? Share your thoughts in the comments below. We'd love to hear your perspective. And if you enjoyed this journey through the mysteries of the universe, don't forget to hit the like button, subscribe to the channel, and ring the notification bell so you never miss out on our next cosmic exploration. Until then, keep looking up and keep wondering, because the universe is full of secrets waiting to be discovered. you.